Welcome, everyone. Thank you for joining in presence and virtually from the Zoom connection. I'm very glad today to introduce you Martin Uhrin, that he will deliver this talk about materials modeling, I would say, and digitalization. That is a hot topic nowadays. Martin, actually, I can share the CV with you, but I want just to summarize that he's coming recently from one of the best modeling group in Europe and maybe in the world. So very active in developing modeling infrastructures, which is another hot topic that is becoming quite popular, for the idea to be a sort of tool for promoting open science with the shared users and so on. So I think that there are many topics that the talk by Martin will cover and will hopefully excite the audience. So and of course, thank you very much, Martin, for your availability in delivering this talk and for joining the Institute and spending some time with us.
Thank you very much for the really nice introduction. And yeah, indeed, for sort of setting landscape, I'm in the group of Nicola Martari, for those of you that don't know, at EPFL. And indeed, the group is very, very large, very successful, does a lot of electronic structure theory and a lot of modeling in general. If anything, I'm kind of the black sheep in the group because especially the last few years, my work has been very much focused on machine learning and trying to interface some of the things the group does with new developments in machine learning. And so I kind of, I sit there on my own and I kind of do things and I reach out to people and see what's possible and take, the latest things that I can find from Google and DeepMind and try and combine them with the things that we're doing in the group and kind of where I think materials modeling is going. So I recognize that probably for many of you, this is somewhat distant from what you do every day. So what I try to do here is to just give you an impression of what I think are the important things that are happening in machine learning, particularly at the atomic scale. That's the sort of area I work most in, and kind of where I think things are going. What are the important technologies and where are they going to take us in terms of the way that materials discovery is done? So the way that I try to do this is almost through my own journey professionally as a scientist, which started in the group. Nicola, I went away to DTU to work at an energy institute, came back to EPFL. And in a way, this reflects my personal journey, but also the way our field has been shifting, the computational atomic materials modeling community, which is that we started to have all this computing power and very, very powerful and robust pieces of software that allow us to do modeling for us, typically at the quantum mechanical level. But of course, we needed to orchestrate, organize, and automate a lot of this in order to take away the laborious work that gets in the way of us actually making discoveries and doing science. As I'll go through in a bit more detail, I went through that journey, spent a lot of time effectively writing code, developing methods. And then we had all this data. So I thought, okay, great. Now let's use this data. Let's do some machine learning. Let's find patterns. Let's actually accelerate this discovery process even further. And then the sort of last part of the talk is sort of forward-looking to what a lot of times gets called generative models. But in essence, this is the idea that maybe computers can tell us not only the properties of a material, but actually tell us, well, this is the list of properties you want. Here is the atomic configuration that should have those. So that's where I think the future is heading, and I'll give an example of that. Okay, so for the first part, really just kind of going back a few years now, actually back to 2013, we started developing, I wasn't yet in the group, but this Python infrastructure called AIDA. Now, AIDA does exactly this job of replacing those laborious calculations that would be scripted up by a PhD student or postdoc. They would do all this wonderful work, and then they would leave and nobody could use their code, and that's it. We had to rewrite it, or someone had to spend a long time figuring out what it does. And that's really a shame. When you think about it, what we want to be doing is doing the science, thinking on a higher level than the level of, what are my convergence parameters? How do I get this thing to give me the right answer? So we created a system for putting together all these workflows. So now a PhD student will write this once, that'll be put in the repository, shared with whoever wants to use it, and reused. And now we think at a higher level. So a lot of things that before we'd have to really put thought into getting, we can now get straight away. We can get band structures, elastic constants, equations of states, all sorts of things by just running a workflow, often with no human intervention necessary. So that's already a big plus. On top of that, we have a lot of codes. I mean, I just took a few, the ones I know a bit better, but there's maybe 30, 40, 50 different codes. You can imagine these are not only codes that are doing the same thing, they also work at different scales. So there are quantum mechanical codes. There are ones that work on higher levels, sort of less accurate levels of theory, but then allowing you to go to more and more atoms. So it's kind of building up this vertical infrastructure to be able to run at different scales. And one of the important parts for me as now a machine learning person is that the way that the software AIDA works is that it's always connected to a database, and it's always storing exactly what you did, including the full sequence of steps. So, I took some structure, so this would be a crystal structure, and I had to put some parameters into my calculation, and I relaxed it, got the relaxed structure out, did some more calculations on it. All of the inputs and outputs are stored, so I can go and pull out things that might be relevant to my machine learning model, or we can even just verify, sometimes mistakes get made or important things get missed. We can go back and look exactly, this result that I published, where did it come from? Well, here, and then even before that up there. And this isn't just in the realm of the computational side, it's also now spreading into the experimental side. So more and more projects are using AIDA as well as other tools to effectively track the provenance of all the things that happened in an experiment, how the material was made, and then how it propagated downstream to all the testing and characterization. And I think this is going to be more and more necessary, and European projects now almost demand this level of information about how a substance was made and what was done with it. Of course, all of this stuff is because of a strong drive from Nicola and all of us in the group. It's made publicly available. It's on our front-end website, the Materials Cloud, where you can see all of the results that we get, the full provenance graphs, the crystal structures, all of the results. You can even run the quantum mechanical calculations there yourself. And this is already being done in more and more experimental groups where now they no longer need the domain expertise. They don't need to come to us and say, can you help us? They can run these things themselves and get the results for at least basic properties without any deep understanding of what the code is doing. And from my side, we spent a lot of time just looking at, okay, well, let's take all of the crystal structures that have been ever deposited in databases, and let's at least calculate the basic properties of all of those. So when you take it, starting with a few different databases, you kind of throw away the ones that are duplicates, and then you sort of massage the numbers and see which ones will actually converge, which ones you can actually get reasonable results for that you can trust. And in the end, now we have this collection of around 40,000 crystal structures that we trust, that we have good basic properties for, and that we can do machine learning on, which is kind of what really started me on this journey. This is now a few years ago. And these are all publicly available, and we calculate more and more properties on these, determine if there are 2D structures that can be made from them, 1D structures, whatever you like. So this is really a sort of gold mine of high quality crystal structure and property data that is invaluable to the community, and without which people like me that now rely on a lot of data wouldn't be able to do our work. So this was kind of my past. There are many people that contribute to AIDA at the moment still, and also now companies. So Microsoft are using it internally, Fraunhofer, Syntact, and so on. So that's really, really nice to see. And I think it's just a recognition of the fact that we need to stop doing this kind of by hand stuff. We need to automate it and think on a higher level. Now, once we have these things, what do we do with them? Well, for me, I mean, kind of as is alluded to by the title of this talk, the physics-inspired machine learning. For many of us that work in this area, we're almost disappointed by what we're seeing being done often in industry, where they deliberately treat the problem as a black box. It's just, well, whatever inputs you can throw at it to the output that you want to predict, and I don't really care what happens in between. That's very, very unsatisfactory to me as a physicist, I think many members of our community. And so what we try and do is put back some of the knowledge, some of the rules that we know have to be true from the laws of physics, in order to make the machine learning models more understandable, but also ideally better performing. They can do more with less data. And it's not obvious that you could get that. I mean, computer scientists will tell you, no, throw away all our preconceptions, just let the black box do its thing. Well, I'll try and argue that we don't actually need to do that. And in fact, we shouldn't do that. So to go into a little bit more detail. So what we're doing here is saying, well, for us, because we work typically at the quantum mechanical level, we know, at least for ground state properties, the Schrodinger equation will describe everything that we can possibly want to know about the system. So long as we give it the set of atomic coordinates, Ri, and the atomic species, Zi. After that, everything is determined by the Schrodinger equation. So what we'd like to do, of course, is to not have to solve the Schrodinger equation or approximations to it, which is what we do, we'd like to sidestep some or all of that because still these are expensive calculations. So for my machine learning model, I'm going to think of it in the same way. I'm going to think, okay, well, I need to give it atomic positions. I need to give it atomic species, put it through some black box. I tend to use neural networks, but it can be linear regression or other regression schemes. And then I want to predict the property that I want to get out. So, but we can already start to ask ourselves, well, what is a suitable input to this neural network? Well, we want something that's going to respect, at the very minimum, the symmetries that we know to hold true for the Schrodinger equation. So to give an example, if I rotate globally a molecule or a crystal, of course, the energy doesn't change. The other downstream properties don't change in the absence of any kind of external magnetic or electric fields. If I move my molecule, nothing changes. If I change the way I label my atoms, instead of calling this one number 1, I change 1 and 2 around, nothing changes. The laws of physics are invariant to these transformations, and we want that to be built into the input that we feed to our neural network. And in addition to that, there are some good mathematical things that we want. So, of course, we want the input to be smooth so that we can differentiate it, continuous and complete, so that any distinct collection of atoms will map to a distinct description, a fingerprint, if you like, of that system. So I wanted to try and give you a little bit of a feel for what this means, because otherwise it's just all maths, and I think that's a little bit boring, especially in a place like this. But let's say, so we want these properties, right? And if I start with I've just taken a random molecule just because it makes things easy. But you can see that, from the point of view of a machine learning model that takes this molecule in, what it sees is, of course, these numbers, the X, Y, Z Cartesian coordinates of the molecule. And if I rotate the molecule, we see that these change. Now, what that would mean for a machine learning model is it would see it as a completely different input. It just sees a whole different set of numbers that it now needs to learn. We as physicists know that this is the same thing as we started because we've just done a unitary transformation of this input. Nothing changes in terms of the properties. So how can we try and bake in some of those desirable features that we want? So for permutation, you might say, I tend to show a little bit of code. I recognize that Python might not be known by everybody here, but I think it sort of removes some of the magic that can sometimes be here. There's no magic going on. All I'm doing here to put in the permutational invariance is, okay, I'm just going to sum over all of the coordinates along all of the atoms that I have in my system. So all the X's, I'm going to sum all the Y's, all the Z's. And you can see that now when I swap them, so you can see the first one is moving down in this array, my output doesn't change. So, okay, so now I have a permutation invariant description. What about translation? Well, now I can just subtract the center of mass of the thing. So before putting it to my model, I just take whatever is the center of mass and subtract it from the Cartesian coordinates. And you can see I'm just translating the X coordinate of everything, and the output doesn't change. So all well and good, we're getting closer and closer to something that we might want. Rotation, we can do something like take the norm. So for all of the vectors, we just take their length and we feed that to the model. So now as I rotate, of course, the length of a vector doesn't change. So all well and good. And now we can put it all together. So now I'm going to center my molecule. I'm going to calculate the norms of the resulting coordinates, and then I'm going to sum them. So now I've got something that indeed is entirely insensitive to these transformations, but I've only got one number, right? Inevitably, because I've just effectively integrated over all of this information. So now we're not having this completeness property that we want. We want something that is that, there are many molecules that will map to the same one number, right? That is a useless input to our neural network model. So we have to do a little bit better. So if we now expand some of this and do a slightly more careful job, we can say, okay, you know what? As is done in density functional theory and a lot of other places to make calculations easier, let's just forget the many-body nature of the system and just treat it as an atom density. So you can think of this as just, I put delta functions, just peaks on where the atoms are, or I put a Gaussian, which is the second line. But in any case, it transforms it from a many-body quantity to just a single body. It's just a density in space. But it still has all of the same information content. I can then expand that in some kind of a basis that I want. Now, it's for various group theory reasons quite useful to work on a spherical harmonic basis, but you can think of what I'm showing here as just a Fourier transform of my signal. And I keep all of it, not just the intensities, I keep the full thing. I keep the expansion coefficients. And so long as my bases are orthogonal, I can get back the original thing that I started with. And so what might that look like? Well, that original molecule looks like this if I expand it in the spherical harmonic basis. And so you can see it's pretty much what we had. We've got some peaks in space. It's now a one-body function, so it's permutationally invariant. And we've got a finite representation, so there's a certain number of Fourier coefficients, if you like, that I've kept and thrown away things after that. And then I can look at, well, what's the effect of throwing away? You know, if I stop it, if I go up to n equals 7, this is how it looks to the model. If I go up, it gets closer and closer to the original, which I've superimposed here. And so we've kind of got this control. We can smoothly get to a perfect description of the thing we started with. Now getting to invariance, so especially the rotation invariance, is a little bit more work, because we're still in a situation where if I rotate it, these are now the Fourier coefficients, if you like, they still change, right? It is permutation invariant, but it is not rotation invariant. It takes a little bit of work to figure out how to do this, but I try to sort of visually represent it by showing you a tensor product between these Fourier coefficients. You can see that they rotate in a very sort of predictable way as I rotate the original molecule. But the one thing that doesn't change is this guy down here. So on the bottom left, there's this sort of yellow pixel that is actually a scalar. So that is an invariant to rotation. And actually, it turns out through a series of mathematical tricks, we can just do higher and higher order tensor products and pull out always the scalar and get more and more and more scalars that describe this collection of atoms until we can actually get to something that is essentially a complete description and rotation invariant. So you can see now I'm plotting all these numbers, but actually as I rotate, none of them change. And I can sort of grow the size of this fingerprint, if you like, this descriptor space, as large as I like to accommodate the number of atoms that I need. Okay, so to sort of summarize what's going on here, I'm going from the atomic environment, so the Cartesian coordinates and atomic species. I put some feature functions, so some Gaussians, say, around them. I do a Fourier transform of that, and then I do some tensor products and pull out just the scalar parts, the bits that don't change when you rotate the system. So this is a perfectly good input to our neural network. So now if we go back here, I might skip this bit for the interest of time, but the one thing I will note is that, so there's been a lot of progress. I mean, in the last decade, it's almost hard to keep up, but even in the last few years, just adding these kinds of tricks in, considering how things transform when you simply rotate and translate your system, can gain us an enormous efficiency gain in terms of the amount of data we need to learn the same problem. So to give just one example, our collaborators at Harvard used a quite modern equivariant neural network to learn the energies and forces of water molecules in various phases of ice. Now, with this new model, which is maybe, so in I think 2020, the Gordon Bell Prize was awarded to DeepMD, so quite a sophisticated machine learning model. They were able to do a 1 million atom simulation using their neural network. Now, just 2 years later, with this more modern approach that takes into account these symmetries, they were able to get the same energy errors. So this table is just plotting you energy errors in, I think, milliev per atom. But effectively theirs, which is the NetQuip ones, when compared to the DeepMD, performed equally well when trained on just 0.1% of the data set. So you can see we've made orders of magnitude improvement in how well the neural network can learn from the data that it's fed, which is great because it still costs us quite a lot to get that data in the first place. We want to minimize that, especially if it's experimental data. So I think these are really big steps that are being made in our community and are important to getting us to that future where we can accelerate materials design in a really meaningful way. Okay, let me give a few examples from the work that I've been doing to sort of show the power in a way where these things are going. So I've deliberately chosen 3 that are quite different in their character. So one where I'm using the machine learning to learn from data that I have from experiment, so no simulations at all involved. Another one where I'm doing something very traditional, where I'm learning an energy landscape of potential energy from ab initio calculations, so the quantum mechanical calculations I mentioned. And then a third example where I'll actually be still using the quantum mechanical calculations, but accelerating a part of them. So it's kind of you're plugging your machine learning into a step that you would normally do, to accelerate this, as I'll show by quite a big factor. And this is kind of, I think, where things are going. It's not going to be machine learning replaces everything in your pipeline. It kind of slots in and can do things, maybe speed up the harder parts of the problem, but still retain the accuracy of the thing that you care about, whether it's experiment or calculation. Okay, so why did I get into ionic liquids? My first experimental example. So I was working at the Danish Technical University in the energy section and surrounded by experts in both computational and experimental approaches to find effectively new energy materials. I was particularly interested in batteries and started working on a class battery called metal air. So these are quite attractive because you just have an anode that is just, in the ideal case, a pure metal like zinc. You've got your electrolyte and then no cathode. It's just the air or some, you've got some matrix that the air can diffuse through your electrolyte and into your anode. And so the energy density of these kinds of batteries is huge because you don't have to count the cathode. In fact, looking at lithium ion, I mean, this number is a little bit higher now. You can see, let's say it's 300 watt hours per kilogram. The theoretical maxima for, depending on what anode you use, can go up to 11,000, or what I was working on, the zinc air is already an appreciable factor greater than the best lithium ion that we have. But one of the big problems in these systems is, you can imagine, you've just got this pure metal sitting there. It's very, very reactive. It really doesn't want to be there. And as you cycle this thing, you actually start to form dendrites from the anode into your electrolyte. And then eventually that will just bridge the electrolyte and short circuit your battery, and then it's game over. So for that reason, you can already buy zinc air batteries that are non-rechargeable today for example, hearing aids, but there are no secondary batteries that are at least commercially viable. So tackling this dendrite formation for all of these systems is frankly probably the biggest challenge. And these room temperature ionic liquids have already been shown to almost entirely eliminate dendrite formation. So they seem like a very promising, viable candidate to use as your electrolyte. Now, what they look like is there are families of anions and cation molecules, and you can effectively play this nice game where you can choose a pair of these and just say, well, I'll make that into an ionic liquid, or I'll make these two into an ionic liquid, and just try and see what the properties of that system is. So for me as a machine learning guy, that's great because I've got this whole zoo of things that I can play with, put together, and then search for ones that maybe haven't been tried before. The problem with almost all of them is that they're very viscous. If you make this thing, it's almost like honey. So you can imagine that's not ideal for an electrolyte where you want to have good conductivity of your ions through it. So the goal, in a way, is just to find a combination of these that have, let's say, lower viscosity and therefore higher ionic conductivity. So here's a part where I think is sort of an example of where we try to inject some of the physics into it. So let's say I make an ansatz. I know that the conductivity is going to be probably governed by the same kind of laws that we are used to, an Arrhenius equation. So what I'm going to do is I'm going to say, okay, instead of just letting the machine learning model learn anything that it wants, I'll say you have to learn something that looks like an Arrhenius law. I'll give you some parameters, A, B, C, that you can learn in any nonlinear way you want. And then I'll sum this I runs over all of the atoms in the system. So it's like I'm going to learn a contribution to the final ionic conductivity from each atom, considering sort of the atoms that lie around it, and then add that with the next one, then the next one, then the next one. And the reason to do that is that that gives you locality. You can imagine molecules, many of them are just like I was showing here, repeating very similar patterns, right? Depending where you are, you'll see similar things, and that part of the molecule will likely contribute a similar contribution to the conductivity, no matter what's going on with the rest of it. So you want to kind of learn from these local chunks and put it all together at the end and give your final prediction. There's good data, reasonably high quality from experiments, about 4,000 data points that give us effectively the ionic liquid, what it is, the temperature that the experiment was conducted at, and the measured or inferred ionic conductivity, let's say. So as we always do, I'll split this into a data set. Now, in order to be fair, I didn't want to be simultaneously learning across different ionic liquids and temperatures, because kind of the temperature relationship is a bit easier. So I'm going to split it into by the ionic liquid type, so which pair of anion and cations I have. 260, I'm going to show to the machine learning model, including across the different temperature range. And 50, I'm going to hold back. It's never going to have seen those. So it's as if somebody discovered a new one and asked the model, well, what's the conductivity of this? The workflow for this model is, well, I start with the name of the molecule, convert it to so-called smile strings. And from that, I can slowly build up the atomic description. So now I know where roughly the atoms should be in this molecule, at least using a fairly basic level of theory. And then I can feed that to exactly those fingerprinting algorithms that I showed you, which then becomes the input to in my case, a neural network, which spits out these three outputs, which are just the A, B, and C for each atom, right? And then I sum it all up for the whole molecule. You'll see a few of these throughout the talk. So these are parity plots where I'm showing the real answer, so what I got from my database versus that which is predicted by my model. Of course, if these were completely perfect, they would lie on the X equals Y line just perfectly along the diagonal. And there's some spread because of, in this case, both model uncertainties and uncertainties in the experiments. But this is already, for me, a very, very good sign. This is just on the training set. So those are things that the neural network has seen. So it's entirely unimpressive that that line is like this because neural network can even learn random labels. But what is, to me, impressive is that the validation also looks similar. As in all cases, it's a little bit broader, so the error is greater there, but it's really very much enough for what I wanted to do. So then, of course, what I did was I played exactly this game. So I said, well, I have these, whatever it was, 310 ionic liquids. They share many different, many common anions and cation molecules, but there are many pairs of those that have never been tried that aren't in any database. So now within a few seconds, I can just ask the model all of those thousands of pairs of anion and cation combinations and ask it, what do you think is the conductivity? And that's what I've drawn here with these vertical lines for just the ones that were very high, because I'm not so interested in the lower ones. And plotted against it is the ones that we have from experiment. These are at room temperature in this case. So you can see I'm predicting a few. So there's a point here and a point here. There's a couple of known ionic liquids that have good properties. But then I'm predicting a whole bunch here that are really up there in conductivity compared to anything that we've synthesized so far. So the goal now is to try and convince my colleagues at DTU to synthesize this thing and see if we got the right answer. And if we did, I think it's quite a big step forward. Okay, the next example is what I would say the more traditional way that machine learning has been used for some time in our community, which is effectively to replace density functional theory or some reference model that you have that gives you an energy. So now you want to train a machine learned interaction potential that knows what the energy is as a function of local atomic configurations, so that you can then run molecular dynamics. You can imagine I learn some energies and forces, and then if I learn those accurately enough, I can just integrate Newton's equations of motion to get what the structure is and the properties are as a function of time. And in this case, we were interested in, this time around, solid state electrolytes. And again, the challenge is always the same, is can we find something that has a sufficiently good conductivity to act as an electrolyte, in this case, for example, for an all solid lithium battery. So what we have is some first ab initio molecular dynamics runs. So these are real quantum mechanical simulations that where we integrated equations of motion for as long as we could, which is about 10,000 steps, if you like, of integration, and at different concentrations of lithium. So you can see we can lithiate or delithiate the structure. And we typically run at what would seem like very crazily high temperatures for reality, but it's just so that we can accelerate the dynamics here. And we want to see more stuff going on in the limited amount of steps that we can do to feed to the model. So when I did this project with my master student, Ji Wang, and so Ji fitted the interaction potential, went through all of it and looked at how accurate are the energies and forces in our machine learning model versus the original reference, which is this density functional theory calculation, as a function of the different concentrations. So these are in units that are a bit difficult to read because they're square of what would be typical. But let's say for the energies, which is what this is, a typical error that our machine learning model is making is about 1 millieV per atom. So the accuracy of the density functional theory, so the quantum mechanical approximation we make, isn't much better than this. It's maybe half that at best. So we're already basically down to the accuracy of our original model. And this is really quite surprising. It was only a few years ago that going down below 5, 8 would really be challenging, especially in a system like this, which has several different elements. And similar for the forces. The forces are really very, very good, very close to the errors that we're making in the quantum mechanical model itself. So what GE did was then, of course, we need to make sure that the unit cell we're using is large enough to capture the conductivities that we want. He did some nice convergence on this, and then we can look at how is the lithium diffusing as a function of temperature. And from the gradient of these lines of diffusion, we can calculate the conductivity and also the activation energy of a typical hopping for lithium, which is particularly attractive because that's something that we can readily compare with experiment. So what GE did was so there's he's showing two different lithium concentrations, the pure, let's say the standard compound, and then one that's been slightly lithiated. And then we plot these Arrhenius plots, which allow us to extrapolate the activation energy for these lithium diffusing around in the lattice. We then dug up some literature and found that actually for both of our values, for the two different systems, we're actually not that far off, which is already quite an achievement. It's not that easy to get numbers that in absolute terms are in strong agreement with experiment. Often we're happy with, even if just the order and the relative numbers are good. But I wanted to see if we could do a little bit better than this. So we dug a little bit deeper into the literature, and we found that actually, so this one has a lot going on, but the relevant line is this one, the 0.396 EV, which, as you can see, the comparison number would be this 391. So actually, we've completely nailed it. I'm not saying that's really a demonstration of the error. I think the error is slightly larger than the difference on these, but we're really very close to the experiment. The reason this number is different, as we found out, is that actually there's different ways you can occupy the sulfur sites in this crystal structure. So there are octahedral and tetrahedral sites, and you can occupy them in different ratios, and that will change your conductivity. So, and this one was actually in a different phase, we think, than what we were working with. So I asked GE to go back and change these occupations to be more like what they were likely seeing in their experiment, 60-40 for this green line. And now, having the structure that we think is the corresponding one for this experiment, the error is again bang on. It's as good as I think it could be. So this was really, really encouraging. I was super happy with this. And I always knew that, so what we've shown up till now is kind of things that have been done. People already know this. But the calculations that we're doing are for the perfect crystal. Of course, reality is like this. There are grains, grain boundaries, defects, and so on. So can we at least, we cannot possibly hope to go to that many atoms to simulate that properly, but can we get closer and closer to that reality? So the first thing I asked you to do is take, if you look at this convex hull, the green dot is kind of where we're at with our crystal structure. So you can see it's not fully stable. It's a little bit up in formation energy, but low enough that you can stabilize it reasonably easily. So I asked you, well, can you run molecular dynamics on the phases that are at least around our point and this final one? Can our model capture these systems correctly? And I thought the answer would be no. But in reality, he said, oh no, these three on the right, we can run molecular dynamics, no problem. Now, the reason that surprised me is because if you imagine what the machine learning model is really doing, it just sits on an atom, it looks around it, looks at where the other atoms are, and says, okay, I think the energy of this thing should be this. If it's never seen a configuration like this one or this one, which it won't have because we're in a crystal structure that has a different stoichiometry, different local environments, it shouldn't be able to correctly guess the energy of these. And yet, in the end, it did a totally fine job. We were able to run molecular dynamics, no problem. And so it's clearly learned something more intrinsic than just a pure interpolation of, well, I've seen something like that and like that, so I guess somewhere in between. It's able to extrapolate beyond that. So it's already showing quite a lot of data efficiency. The last one here didn't work at all. So within 100 time steps, that would just blow up because the forces were so bad. The cell would just tear itself apart. I'm not sure why that one in particular. I don't know if it's just bad luck or if it's really due to the fact that it is quite different from the other compositions and the local atomic environments are quite different. Something we need to look into more. So I was already happy with that. And then I thought, okay, great, then I'm fairly confident in going to the next step, which is to at least look at a grain boundary. So we take our crystal, make it bigger, cut it in half, put it together, in this case for this grain boundary configuration, and then run the simulations again to look at the conductivities. And what you found, surprisingly little, these aren't very well labeled, but the orange is the original data, if you like, and this green one is the data from the run with the grain boundary in it. So actually, the conductivity in this case, which would be related to the slope of this graph, is higher, which is kind of weird. So you've got this grain boundary, which I might naively assume that when my lithium reaches, it's going to have a harder time crossing. But in reality, it's also possible because for now, we just measure the conductivity averaged across this whole thing. You also have the fusion that can go along the grain boundary. And it's likely that this is at times easier than actually trying to cross the boundary itself. So that could be contributing to this overall result. The next step is to, of course, pin this down exactly, look at the transport longitudinally and along the grain boundary, and then try many different grain boundaries, see if we can actually understand statistically what does it look like and correlate that with what's going on in the real material. Okay, the last example I want to give is from the class of the machine learning model where instead of throwing away the experiment or throwing away the calculation, quantum mechanical calculation, we want to keep it, but we want to replace a really, really slow and difficult part of it. So there's quite a technically involved problem with the approximations that are made in, let's say, the vanilla typically used density functional theory calculations. So these are really solving an approximation to the Schrodinger equation. But one of the shortcomings that they have is that they very poorly describe elements that have a strong D character or F character, right? They tend to kind of over-localize electrons and then give a lot of bad properties. The lattice parameters are often quite off. The band gaps are off. So a bunch of people in our group, Matteo Peccocioni, Yuri Timiro, developed what has become known as the Hubbard corrections to density functional theory, which try and correct exactly this problem. So that can help, but it's a very, very expensive fix, if you like. So to give you a little bit more impression of what's going on, if you imagine we have let's say we have some expression for our energy that comes from these calculations. We now want to correct that energy to try and fix some of this problem that the approximation caused in the first place. And there's two numbers. These are just scalar numbers that come into play in this, called the U and the V. So if you ever work in this field, you'll always see people talking about the Hubbard U or the Hubbard V parameter. Loosely speaking, what these are doing is the U parameter, this number, the higher you make it, the more you will favor your electrons being localized onto your atom. So you will correct some of this problem, but you'll actually overcorrect it if you just do that. You need to introduce a V parameter, which acts between pairs of atoms to actually try and hybridize the states back a little bit. So you actually correct both parts of the problem. And there is a good theoretical underpinning. I'm not really doing it justice here, but if anyone's more inclined, I highly recommend the paper by Matteo Peccocioni. Effectively, this is based on the idea that density functional theory makes an error when you look at fractional occupations of the electrons sitting around an atom. So we know that these should be piecewise linear as you increase the amount of electrons, let's say, sitting on an atom by a tiny bit, not an integer amount, but a fractional amount. The DFT will actually give you a spurious curvature here, so a quadratic form. So we want to subtract that quadratic part to just leave a linear term, which we know from the physics is the correct thing to do. So that's why you see this term here. It's just NN. That's the quadratic part we're subtracting in the U, and same with the V, and we just leave a linear part, which is what this thing is doing. Now, what are these NNs? These are just, if you think about it, we have our charge densities, so our electrons sitting around all of our atoms, and we want to localize them. We want to look at just a chunk around an atom. So we project these onto spherical harmonic bases. So these are kind of like the very typical orbitals you see for hydrogen. We project all that and we say, okay, I see. So the D states look like this in the system, or the F states look like this. And that's what these occupation matrices represent. It's really what are the electrons doing at a D state or an F state in terms of the occupation around that atom. So these things, the U and V values that correct for this, they can be calculated fully analytically, no approximations needed, but it's very, very expensive. So it will typically cost you around 20 times a normal calculation to calculate those values to then plug back into your system. But the story actually gets even worse because you have to take your atomic structure, make a guess for the U and V, allow it to relax, recalculate your U and V, and then check, hold on a minute, have they changed much, the U and Vs? If the answer is yes, then you need to actually go back around this loop and recalculate, re-relax your atoms, and pay this cost each time you go around this loop. So a typical calculation for Uri might look like this, where you do several iterations until you say, okay, you know what, from here to here, the U value in this case didn't change much. So we're now self-consistent. The U and the energy and the structure are all consistent with each other. So here, if you're doing 4, you know, that's going to be an 80 times cost. And typically you might even do more, 5. So you're paying 100 times the cost of a normal calculation. So can we speed up this thing with machine learning? So can we just take the U and V values, have a guess, relax the structure once, get the machine learning model to tell us what they should be without paying that price, and then just relax the structure last time, and we're done. So I developed these 2 models. They're 2 separate neural networks that now calculate this U value and the V. And these schematics are here just to show you what's going in, really. So yes, your guess for the U that you started with, which can be just 0 if you just don't know. You just say, okay, it's 0, I don't care. The species that you're looking at, so whether it's nickel or iron or manganese, whatever it is. And then the 2 occupational matrices, these calculations have spin polarization, so there's spin up, spin down. And then we pass through these non-linear neural network parts. So this is very much the same as you see these diagrams like I've shown, where you have your neurons arranged in layers. That's what's going on here. And then I get my final U value out from this. And same for the V, except it's now complicated by the fact that you have 2 atoms. So you need to put in both of what the electrons are doing around both of them and their species and the distance between them. And we get our final converged V value out. So I had a bunch of training data from Uri and Luca Vinci, mainly. So these are these very traditional lithium-ion cathodes, so LiFePO4, something you can easily buy, many of these. So these are good starting points, and then some layered materials and some rare earth nickelates. So we have quite a diversity of electronic structures, so what the electrons are doing around the atoms, and that's what I wanted. I want to span as much of the space as I can. And when I train the model, and this is already on the validation data, so the data that the model has never seen, I'm getting errors that are, okay, 151 millieV per atom. Well, what does that mean? Well, if you think these values are like between 5 and 10 or 11, then 0.15 is already a very good result, more than enough for what is typically used in these self-consistent calculations. The story is pretty similar for V, except the spread is slightly worse, but it's still very much good enough for what we need. And keep in mind, you know, yes, it takes quite some time to generate this data. These aren't cheap calculations, but then to run these is now of the order of a millisecond to get your answer, and then you run your calculations. So we've thrown away that cost of 100, but only if we can trust the model, right? Because of course we'll be going to things that it's never seen before. So can it extrapolate beyond the training data that it's seen? So one thing I tried is, well, I took these olivine structures, these LiFePO4, LiMNPO4, and these numbers just represent the total number of training examples I have at each concentration of lithium. So for each one, what I'm going to do is I'm going to take, for example, just one of these and train the neural network model on, say, x equals 0, and then ask it to predict all the rest. And take the other one and ask it to predict all the rest. And I'll average over all those, and then I'll show it 2 out of the 5 of these, and then I'll show it 3 and see how is it able to extrapolate away from just seeing one of these to all of the others. So in this LiFePO4, when I show it 1, it's already at a fairly good number, 0.5. By the time I show it 2 out of the 5 of these, it's already doing very, very well. Almost as well as if I show it 4 and I'm only predicting the last 1. So that tells me, okay, great. So actually and it's not obvious that this should happen, because if you imagine, depending how much lithium there is, the oxidation state of these elements is going to change. So the electronic structure is really quite different. In reality, it's already enough to show it 2, and it can extrapolate successfully to the rest. Similar story for the manganese. Actually, I'm doing myself a disservice here because you can see the scale is only up to 0.8 here. So this looks worse than that, but actually it's much better. So we can actually already just take one of these and it will be able to predict the rest. Okay, so let me move to the more forward-looking part, which of course have slightly less results, but I'll show you something that I find interesting and I think is an important addition to our toolkit as modelers. So everything that I've shown here is kind of doing this, what I think of as the sort of Edisonian way, right? So you want to make a light bulb, you need to find a filament that can survive for long enough. You're just going to try lots and lots of things in the periodic table. And now with calculations, that's particularly easy. And I'll just look for the ones that have the properties that I want and maybe do a bit more careful checking around those, and we're done. Of course, what we'd love to do is to go backwards, right? So we'd love to start with the properties and then ask the generative model to tell us, hey, what structure, what elements, what should I put in this thing? And this would be the actual model types of the generative models. And the general field is, of course, inverse design. And I think this is where things are going, but there's a lot of steps that are needed, a lot of effectively breakthroughs that are needed to get us there. So one system that I decided to tackle for this in this kind of realm is glassy systems. So of course we know that these amorphous structures, they're not entirely disordered, they don't look like a liquid, but they're not like a nice crystal where we have some kind of unit cell that repeats, maybe with grain boundaries, but at least it has a unit. No, there is disorder, but within the disorder there is order. There is some statistical correlation between where the atoms sit next to each other. Now, just as an experiment, actually, I was being shown one yesterday. One of the ways that we do this computationally is that we have to do effectively simulated annealing, right? We have to heat up our material and then quickly quench it at some quench rate to try and freeze it in an amorphous structure that we hope is stable. And a lot of the time, we find that actually, no, that isn't the right one. The radial distribution functions we have from experiment don't match, or it's actually not stable. And you spend a lot of time doing these very expensive calculations, choosing different quench rates, and depending on the system, it can be a bit of an art to even find your final structure. And remember, that's just even the starting point. Once you have that structure, then you can calculate properties of it, do things from that building block. So it's really something that would be great to accelerate. So what I tried to do is to take and in fact, I kind of had this in mind when I did this work, this sort of rotationally invariant fingerprint of these local atomic environments, and say, well, can we borrow machine learning models that can help here? This particular model that I've used is called variational autoencoder. Well, what you can imagine it does is it's a neural network that takes my inputs, which is now going to be this rotationally invariant representation. The number of neurons in each successive layer gets smaller and smaller until a bottleneck, which you of course converge. You find the minimum size bottleneck you can find, and then it opens back out to give exactly the same output as the input that you put in. So you can imagine the reason it's called an autoencoder is because it just tries to take the thing that you've put in, compress it as tight as it can go, like a zip file, and then back out. Ideally, it's not going to be lossless ever, but ideally you train it to give you as good an output as you want, as accurate an output as you want for the input. Now, the reason you would want to do this is because if you're a little bit careful in the way you structure the Z, which is called the latent space, you can actually then throw away this part and just sample from your latent space, and it will give you samples that kind of look like your original input data, but are novel. They're entirely new. And if you've ever seen the kind of algorithms that, take a bunch of faces, and then you ask it, give me one with, brown eyes, blonde hair, age 60. It's never seen an example of exactly that, but it will give you an output that looks quite realistic. And it's doing that through a mechanism like this, through interpolating between the pictures that it has seen. So, of course, for us, that's a good start, but then what we get out is a fingerprint, so we still need to go backwards. And that's one of the things I spent some time trying to solve, which wasn't really an obvious problem. Once you have these rotationally invariant representations, how do you go back to the original fingerprint that you had? So let me show you these. So we're back to this fingerprint that I have, and now I need to go back to my atoms. So what I'm going to do is the easy part is effectively finding where the atoms are in this sort of signal, this rotation invariant, this permutation invariant signal. You know, wherever the peaks are, that's probably where my atoms are, and I can build an algorithm that iteratively finds one after another after another. So that's what this function is doing. It's basically taking the atom density and it's found these orange dots, which are at the maxima in this density, if you like. And that's indeed exactly where our atoms were from the original. But the step before that is actually a bit more difficult. So what do I mean by that? So going from the invariance, which you can think of as being similar to the intensities you get from an X-ray, right? So you know that once you get this diffraction pattern, you still need to do something to get the atoms back. And that's because in that case, you've lost the phase information. So you don't have everything you need to get the original atomic structure. Here I'm doing effectively the same thing, except in spherical harmonics rather than plane waves. And I invert this numerically. So I sort of get the answer that I think I need, and then I do gradient descent to try and find, well, what would the signal look like if it was the answer that I know that I should get from the invariance, until what it's predicting from the atom density exactly matches the invariance that I have, the fingerprint that I've come out. And I've done this procedure here, and you can see there's a little bit of noise, but it's really good enough for what we need. The other interesting thing is you can see it's not aligned in the box in the same way that it was originally. And this is entirely expected because we threw away all global rotation information. We're just stuck with the invariance. So of course, what I get back will be some random orientation, but at least the internal structure of what the atom density looks like is correct. And so I have this iterative algorithm that goes around and tries over and over and over again to get closer and closer to the answer until it finds the original atomic configuration that we started with. Okay, and so once we have this tool, we have everything that we need. And working with another student, Anna Pavlish, I asked her if she could try building one of these autoencoder networks, decode from the latent space, apply the algorithm that I just described, find the density grid, get the atoms back, and then let's compare with what we originally started with. So, for example, the radial distribution function from the original data, in this case, it's amorphous silicon, looks like this. And this is ours. Now, it's far from perfect, and we have this spurious peak here. So this is the same scale and distance. So this shouldn't be there at all. And that comes from this step where we sometimes mistakenly put two atoms closer together than they really should be. So we have already a fix and it works for that. But the rough peak of where this thing is are in the right places. So we're already getting close to being able to predict the right structure. And we have ways where we can already incorporate the radial distribution function, not only from here we know where the atoms are, but for example, even if we don't know them, for example, we get this from experiment, we have ways to feed that into our model and train it just based on that. And then, of course, the next step, which we already have in the works, is to build an entire unit cell, an entire box of this stuff. Not good enough to just have one chunk. So we put some down, we move our focal atom to another one in the environment, and we build the rest of the missing atoms, and then move and build the rest of the missing, and we can build as big a box as we like, effectively for free, especially compared to doing these quenching simulations. So that's so far one of our contributions that we're working on to this inverse design paradigm. Okay, let me wrap it up there. So as you've seen, I've kind of tried to lay out this journey of some of the ingredients that are important, obviously through my own personal lens of things that I've worked on. The materials informatics side, where we can just stop thinking about how do we do the nitty-gritty calculations and just get the answers that we want. I think this is a very important field and the one I'm most excited about. How do we put in the physics, enough physics into our models that we get much better performance, but not so much that we, really bias them towards our own human biases, because we should be also careful not to do that. And then the generative model side is just getting started, and there are a bunch of projects we have in the work to do more and more of this over time. And I think we'll start to see this become a sort of integral part of materials design in the next decade. Okay, let me just thank the people that were involved in this. DTU, all the stuff in the ionic liquids was done with Jin Chang, who supervised me at the time, Thijs Vigge, the head of our section, EPFL, of course, Nicola for all the support. Saya worked with us on the solid electrolytes that I showed. Anna did the variational autoencoder in G, also the work on the solid electrolytes. the representation work and equivariant neural networks I do with Ted Schmidt and Mario Giger at MIT, and Thomas Hardy at Sandia National Labs. Lastly, let me just thank a lot both Eliodoro and Pietro for inviting me, and to all of you for making me feel welcome here. It's been a real pleasure to see what's going on at INRiM.